When you showed the initial mass function for stars near the start of the talk, they increased in frequency as you got to smaller masses, but then plateaued around 0.1 solar mass, I think.
Yes.
Why doesn't the frequency continue increasing at low masses?
That's a really good question. And again, what happens at the very low mass end is definitely also an area of active research. So the question was, we had this initial mass function where there was a slope, and you get not very many massive stars and lots of low mass stars. And in both my cartoon and the model, it sort of flattened off at the top and didn't keep going. So why is that? Well, I think the most basic way to answer is when objects get low enough in mass, it's really hard to make them. Right? If I'm going to make a star, I need enough material for gravity to squish that cloud to make a star. And if I want to make a low mass object, I need a low mass cloud, otherwise the star will get big. And eventually the mass of the cloud just isn't big enough for gravity to win and squish it. So that's one reason. But as I said, there's debates, right? People use something called micro-lensing to try and see very low mass objects, even planets that are not orbiting a star. We call them rogue planets or free-floating planets. And there's a huge debate as to how many of those there are. So that low mass end, we don't really understand its shape that well. Some people say there's another little bump.
Yes, so the massive star you used as an example had 8 times the radius of the sun and 40 times the mass of the sun.
Yes.
Which means it's much less dense than the sun.
Yes.
Is that because of the distribution of elements inside it, or why is that?
Yeah, good question. And if you ask probing questions like this, you'll quickly find the limits of my knowledge. So yeah, the interior structure of massive stars is still like an active area of research as well, actually. But yes, they have a different structure. So the which way round is it? I think in the sun you have what's called a radiative core, where the pressure support is radiation driven, and a convective outer layer. Whereas in massive stars, it's the other way round, and I think that contributes to their sort of mass size relation. I don't have a deep understanding of the interior structure of massive stars. So it's less to do with their composition, I believe, and more to do with their sort of internal thermal process. You know, the pressure distribution is different inside.
Yeah, yourself.
Yes, when you explained earlier on how when you have ionization, the electrons fly off the atoms. Where do they go? And do they recombine? And would the fact that you have a lot of electrons recombining or not, I'm not a physicist, so I don't know. Yeah. Would that also affect, therefore, the environment and maybe the type of planets or stars that are created afterwards?
So that's a really insightful question, yeah. So the question is that, I've said that UV light can rip an electron off an atom, but that atom really, really wants to get an electron back. It's not in a particularly comfortable state without its electron. It wants to get another one to be in charge balance again. And it's completely right that electrons do stick back to the ions. But what you have is there will be a volume of space where there's so many of these ionizing photons, ionizing light, that things stick back to the atoms, but then are immediately re-ejected again. So if you look at it in sort of a time average sense, the thing is just staying ionized. And then, a bit further away where the gas is neutral, I'm not saying that the ionizing photons never get there, but they do it so infrequently that the things would recombine. So you're right, electrons do stick back to ions, but there'll be a region of space where they do so for such a short period of time because they immediately get launched off again.
Lovely. We've got a question from the balcony. So Sophie, as you head up to the balcony to get that question there, your colleague Katie Chloe used the same demonstration, and she talked about that demonstration being not space, but the curvature of space-time.
Yes, yeah.
So whilst we've got some time, what's the relationship between stars and time?
Stars and time? In what sense?
Is there any relationship?
I'm not entirely sure I follow the question, but I mean, so stars... What, in terms of their evolution?
So in terms of if you're closer to a star, do you experience time differently?
General relativistic effects here are negligible. I don't really care about general relativity for anything I do. It's a very, very small effect.
Lovely. Questions at the top.
Hello, up here, 1 o'clock.
Yeah.
Hello. Thank you for the talk. I would want to ask you to elaborate a bit more when you said... when we were looking at the elements forged at the core of the stars, you mentioned that once you get to iron in the core, it takes more energy to fuse iron than it gives away. So that's why the gravity wins this balance, and then they collapse. Could you elaborate more on that? How do we get the other elements? Is it in the supernova?
As I said, you can make heavier things than iron, and they are produced in the star, but you don't get any energy back in doing so. So some heavier elements are produced in the core of the massive star. But yes, as you alluded to, a lot of the heavy elements are produced when the thing goes supernova. So specifically, I mentioned that the core collapses, stuff pours in, and you get that exotic process that I know very little about, where electrons stick to protons and make neutrons. Well, those neutrons are an ingredient in the nucleus of an atom, and heavier elements than iron have bigger nuclei, right? So this gives you essentially a big pool of stuff to make large elements from. So that's my naive understanding of where these heavy elements come from.
Gentleman here.
For the paper that you mentioned in the second half of the talk,
yes.
How do we verify the hypothesis presented in the paper? Do we need to gather data from space telescope or ground telescopes? Is James Webb Telescope enough for gathering the data, or do we need something bigger?
Right, do you want another This is what I'm very interested in, right? So the question is, how do we go from a model saying we think planets might be affected by their environment to actually proving that? So there's so many different things we need to do. So from the observational side, we need to understand when the disks, there's a question which is, when do disks actually get exposed to UV light? They form in a cloud, so they're protected at first, always, and then soon after, or at some point after, they're exposed. So for that, we need telescopes to look at real regions and count, what is the fraction of stars that are embedded? How old are they? One of the things I'm doing that I'm interested in is looking at very young regions, because then if you see anything being destroyed, compared to our model, it's on a time scale where it's going to affect the planets. So that's one level of it, is we need to look at the disks in lots of different regions and understand when they actually start getting destroyed. I mean, the planet formation detail side of things, I think that's a fair way off, being able to actually, prove that, some pattern we see in the planets we find is set by the environment. Bear in mind that pebble accretion model, we still don't really have to prove that on its own, and here we're just taking that popular model and seeing how it's affected. It really is baby steps at this point. But I think what I will be doing is a combination of simulations and trying to get new observational data as well. Hopefully at some point there'll be a test.
Hi. If you have a body that is being sandblasted by that ultraviolet radiation, does it strip away particular elements first, so you end up with a sort of a carcass of, shall we say, denser or more interesting elements left behind?
That's a very good question. So when you destroy one of these planet-forming disks, you drag away gas. That's the main thing that gets dragged away. And I haven't really gone into this. I've actually said the word a few times, but the other component of clouds and these disks in astrophysics is something called dust. And you can imagine dust is just like grains of sand. And they're really important because they're what stick together to make our pebbles, and which eventually make the cores of giant planets or the terrestrial planets like the Earth. So when you drag the material away from a disk, you're dragging mostly gas and also small, like sand-size grains of dust as well. But once the dust gets big enough, you stop dragging it. So you're right in that you can potentially save quite a lot of the solids because it's mostly the gas that gets dragged out. But that's another thing that needs to be properly understood. So Lynn's model, that's essentially what we were doing, was saying that the small solids will become big solids after some time scale, and whether or not you start destroying the disk before or after that time scale is really important for the planets you get.
Hi, I was just having a think about magnetism, and you mentioned that these massive stars, create ionized gas. Is the sort of magnetic effect of the star dominant, or is it more the radiative effect that affects the sort of shape of the gas?
Yes, that's a good question. So, what kind of scales? The magnetic fields affecting the star-forming regions, or the disks being destroyed, or anything?
So more the gas that's surrounding the massive star.
Okay.
Is the shape of it affected by the magnetic fields of the star?
So the range of influence of the magnetic field of the star itself isn't very far. But magnetic fields definitely do play lots of important roles in like the ionized bubble. It's thought to play potentially quite an important role. You also do get magnetized winds from the disks as well, which are studied as a completely separate field almost. So I'm not really giving a great response to your question. I think the answer is that nearby to a massive star, the magnetic field's not doing very much to the surrounding gas particularly, but magnetic fields are important. There's things like if you get one of these filaments, if you align your magnetic field along the filament of gas and shine light on it, that helps resist squishing it, for example. So magnetic fields have lots of different important roles. But very local to the massive star, everything's just hot. It's not affecting things very much.
We'll go to the gentleman. Let's go here.
How much computational power do you think it would need to simulate? That star, the galaxy simulation you had where you were plugging in fake numbers because you couldn't.
Yes.
How much computational power would you need to actually be able to do that?
That's a really, really good question. I think we're not that far off, actually. People are... could you do it with modern computers in a reasonable time scale? I think the hardware probably exists now to be able to do it if you're happy to wait for long enough. No, it doesn't if you're getting down to doing the star formation properly, actually. I mean, bear in mind that these are like a three-dimensional calculation. So you've got like a 3D space. If you want to double the resolution, so make all your boxes smaller, then it's going as like, every time you double it, you're cubing the number of boxes you've got. So it's really hard to scale down. So, I think it's not realistic to just run a very big calculation just yet. So some of the things people are doing is like taking a model of a galaxy and using that to zoom in. This also gets over this issue of having a sphere for your starting conditions. You can actually take a model of a galaxy, zoom in, and see what would have happened in higher detail, and then zoom out again and try and link the two that way. But that's a really good question. I think we can't rely on computers just getting bigger. I think it's going to take a little bit longer, and we have to do other things in the meantime than just wait for a bigger computer to hit the nail with.
Why do galaxies and solar systems end up being like a flat disk shape?
Great question. You just love my dancing. I'm going to have to do some more. So imagine a spherical cloud that's trying to collapse. It's a sphere, and gravity's trying to squish it. Nothing is ever going to be a completely static sphere, right? It's always going to be rotating, just along some direction. It's going to be having some sort of rotation in one direction. And the dancing demo is the classical, ice skater or ballerina, right? Where they start off with their limbs out. Hopefully I'm not going to fall over. They spin and draw their limbs in, and that spins them faster, right? It's conservation of angular momentum. And it's better if you're doing it on like a spinny chair or something. That's this length, right? As I move this length of arm in, I spin faster. These clouds are huge. They're parsecs in size. That's 1 with 16 zeros after it meters in size. I don't know what that is in some more comprehensible number. These are big. And so when they do that with a tiny bit of rotation and come down and down in size, they spin faster and faster and faster. Now when something spins, this is coming in handy again. When something spins, there's a force pushing that buzzer outwards, right? A centrifugal force. Don't hit myself again. And so that's going to help oppose gravity. So this thing's spinning really fast now. Gravity can squish in the direction it's not spinning really easily, but it can't squish very easily in the direction that it's spinning, because that spinning force helps oppose gravity. So that's why things end up as disks. And that's what I could answer.
And for the sake of the audiences, what I've been to previous RI lectures, what I've been told that gravity is not really a force.
It's not what, sorry?
It's not really a force. What do you exactly mean when you're saying gravity then? Are you talking about the
gravity is a force to me. Not into GR. No, for me, gravity is just a long distance force. It depends on how massive an object is and how far away you are from it.
Okay.
And that's good enough for me.
Okay, fair enough. Gravity is a force in this context.
Yes.
Okay, let's go to the next person.
There's plenty of, most of the people at Queen Mary giving talks are talking about something to do with gravitational waves or cosmology. So there'll be lots of chances to ask those kind of questions to those people.
Thank you for that talk. It was great. I'm going to ask you such a different question, and I apologise in advance. So as a complete novice, I've just spent the last hour almost having a bit of an existential crisis about the scale of these things, about the distance, about how there's so much going on outside of our solar system. So what is that like for you, as this being your career? Do you ever think about these kind of big existential questions, or do you kind of just look at numbers and you can kind of remove yourself from that?
It's a good question, and I don't want to go on too much of a tangent, but I had a really interesting experience when I was at Cambridge for a while, working with some artists, and it was really interesting to just talk about how we approach our work, and we realised actually we're way more similar than we realised. Anyway, so yeah, I think big numbers you kind of get a bit desensitized to. They become intuitive, so I can like say, oh, something's 10 parsecs, that's big, and it means something to me. Or temperatures and timescales, they become familiar because I've worked with them so much. But I do often have to remind myself to, walking home in the winter, actually look up a bit, because I spend most of my day in front of a computer. If I use a telescope, I write a proposal, which takes me time in the day looking at my computer, and I send it off to a committee that says, yes, we'll look at this, and then they send me the data. And so it's not sort of stargazing these days so much. So it is important to, I didn't say this. I did have some slides in. I don't know if I can quickly find them, probably not. Actually, let's just play it and go back. So these evaporating discs here that I showed you the pictures of, oops, gone too far, oops, by far. Is it going to work? It's not keeping up. Well, it doesn't matter, but I showed you those cometary evaporating discs. They're all actually situated in the bottom of the sword of Orion. The constellation Orion, 2 stars, 3 stars and a belt, and then a sword. Here we go. One more. These guys are all in that bottom of the sword. So one of the things I absolutely love is being able to look up at the constellation of Orion, see the bottom of the sword. There's a massive star there destroying the surrounding gas, and there's these little stars trying to make their planets. So those are the things that rein back in the reality of it to me sometimes, because you do kind of get desensitized, just working on it as a job 9 to 5 or whatever hours we do.
Yes, sir.
I am slightly surprised we haven't heard the word dark today. Does dark matter or dark energy play any role in these models?
Yeah, I'm intentionally not. You look at the RI playlist, and there's so much on black holes, so much on dark matter, so much on dark energy. I personally, they are interesting because they're mysterious. But when I think about, what can we do to address that? Nothing very interesting in terms of what I do jumps out. You're part of a huge collaboration. I love this kind of science because, we can come up with the models and the simulations that we can go and measure and test. So it's sort of what physicists say to me about astrophysics generally. I want to be in a lab touching my sample. To me, dark matter, it's not that important. Well, we know for sure it's not important at the scales that we're looking at here. Okay, for galaxy evolution, that part of the talk, it is important. But for planet formation, dark matter's not going to be doing anything. It is interesting and it is important to understand, but there's a heck of a lot more to astrophysics. I'd argue the range of influence of massive stars exceeds that of dark matter.
Do you believe in alien life?
Had to happen. Had to.
So no, that's a fantastic question, and I think yes, it's extremely likely. You look at all those planets, we're not even finding things down where we expect to find life. One of my other interests now at Queen Mary is trying to start some new collaborations on astrobiology. And we start all of our proposals with, this isn't crazy anymore. We're now finding, we're finding planets. We can actually look at their atmospheres. So if I shine a torch at you and put a planet in front of it, the light goes through the planet's atmosphere. So we can see what its atmosphere is made up of. So if you have a species like us polluting that atmosphere, maybe one day we'll see something. So what we're interested in at Queen Mary is how photosynthesis might work on other planets, because we have a lot of biologists who are experts in that. So I'd say yes, absolutely, and probably in my lifetime, I reckon we'll argue over some evidence that we've maybe found some as well. Yes, that's a good question. And so the question was, because the mic didn't work, we've got massive stars forming, and eventually they get massive enough that they are starting to heat their surroundings and blow away the gas. Is there a theoretical upper limit on how massive the star can be? There is, if you had the star trying to get material spherically, so just material falling from a sphere, then there's an upper limit, because eventually the light from the star would just stop it being able to fall in. You know, the radiation force on the gas will match the strength of gravity. And I forget what that limit is, but it gives you a certain mass. And then we go and look at real star-forming regions and see stuff that's way bigger. So that was a mystery for a while. And the way you solve that is by, like the low-mass stars, so until very recently, like the middle of the last decade, there was a question of how do massive stars form? Is it like low-mass stars with a disk, or more like a monolithic collapse is the special term for it? And it seems that the answer is that they form from disks. Now, if you've got a disk, that helps you, lots of that energy, like with the explosive from the light, just gets out of the low-density bit, perpendicular to the disk, and the disk can get close enough to make the star grow. And so that overcomes this theoretical limit and lets you grow pretty big stars. Like we see stars that are more than 100 times massive than the sun, which we didn't expect to see.
Amazing.
When you were doing your simulations of galaxies, I was looking at it and thinking, well, what happens at the center of the galaxy? As I understand it, there's a black hole, and then you've got sort of a sphere that's almost out of the plane.
Yes.
Is that because they're not spinning as fast in the middle, so you get this sort of ball effect around the black hole?
Good question, yeah. So galaxies have, if you're looking at them edge on, they have a central galactic bulge and they have a thinner disk. I don't think that the dynamics of that, so I'm going to not give you a very good answer because I don't really know off the top of my head, but I don't think it's correlated to the black hole, that bulge. I think it's got more to do with the age of the stars and the fact that, as you saw in one of those simulations, the stars are getting thrown out on all kinds of trajectories. So I think that's just an older, yellower, part of the region which has just had time to, I'm going to use technical terms as I'm getting defensive and not knowing what I'm talking about as much, but dynamically relaxing, right? The clusters of stars have had longer to spread out. Yes, so when I said that we tune the supernovae to get the right answer, some of the things that are criteria for right are the thickness and size of the bulge and the thickness and size of the main star-forming disk, yeah.
Okay, last question of the evening. Off you go.
What would happen to a protoplanetary disk which didn't have a significant effect of radiation pressure from a nearby large star?
So they get really big. So the sizes of the disks in these low-mass star-forming regions, they can be huge, absolutely ginormous, and they're really massive. So I would say they probably just make lots and lots of planets, including some very, very massive planets. So one prediction might be that stars trying to make planets in harsh environments might not make any really massive planets, say, because they just don't have enough material. But maybe these ones in low-mass star-forming regions where the environment's calm, giant planet factories, maybe. So those are the kind of predictions we can make and maybe go and test.
Oh, can we please give a round of applause to our speaker? Thank you.